Okay, so I think we can start. So we have been talking about morphisms, and just start with where we are. So we have to introduce polynomial maps. I don't review the definition of morphisms, I hope you remember. So, but just as I'm using this, I just say, so if f0 to fn are some homogeneous polynomials, of the same degree, with no common, and so, and x is in Tn quasi-projective variety with a zero set of these polynomials intersected with x is empty, then we get that the map f0 to fn from x to indeed, so should be precise n, so n to here is a morphism. Where the map is just the usual one that I sent a0 to an, so this point in projective space, to no, that's the 2 0 of a0 to an, and to f1 so this we saw the last time. The general definition of a morphism from projective variety to the projective space or another projective variety is more general. This is a special case which is particularly simple. Not our morphisms from projective variety. Another one, our X4. And so let's just look at a couple of examples. So just to, for instance, take the map phi from P1 to Pn, which just is sending point E0, E1 to all, I would say, monomials of T3n in E0 and E1. So this means E0 to the n, E0 to the n minus 1 E1, and so on until A1 n. So this is a morphism because I can write this as a polynomial map. This is just x0. So if x0, x1 are the coordinates, here's just x0 to the n, x0 to the n minus 1, x1, and so x1 to the n. And we see that obviously x0, these don't have a common 0 on E1. Okay, in fact we can look at what's the image. So it's actually, if I put say for the image is what I claim the image is the zero set of the following polynomials. I can take, say, y0, y2 minus y1 squared, so if the yi are the coordinates from Pn. Then similar y0, y4, y3 minus, say, y1, y2, and so on until y0, yn minus y1, yn minus 1. Can take the zero set. Now, if you look at it, it is clear that P1 is mapped into this because it's just says, no, this is just, yi, it's just a0 to the n minus I times a1 to the I, and then obviously this will always work. And the claim is that the image is precisely that. And I mean, you can just, so you can somehow easily see that if you have this, if you have something in this set, in the zero set of this thing, you can write it in this form. Particularly, you can see it because you can look at the inverse map. So the inverse morphism is one thing I should say that so the inverse morphism is just I could just write, if I put the coordinates y0 to yn, it's just a map y0 y1, so restricted from x to b1, so we just send the tuple e0 to the, I mean, if I look at the image, e0 to the n, e0 n minus 1 a1 and so on will be sent to e0 to the n e0 to the n minus 1 a1, which is just e0 a1. So I now told you, if I start, first I have here, the first map would be, I map a0 a1 to this, and then these two compositions are the identity. You would also have to see if it works the other way around. And I also kind of leave it as an exercise to check that the image is precisely that. If the image is precisely that, so this is a closed subset, it's easy to check. I will also say it later that if you start with something irreducible, then the image of the map must be irreducible. And so this will therefore be an irreducible closed subset, and so therefore it's a variety, and we can talk about the inverse morphism. So that's so this is, I mean, it's just an example, but this thing, so x, we call it n, and the n is called a rational normal curve. So somehow it's a nice example of a curve. It actually is some kind of extreme example of something. So, but I cannot really later explain. Okay, let's look at some other cases. So, one also very elementary example of a morphism is a say, call it a projective transformation or projective change of coordinates. So this is just the following. Let's take any square matrix A. So E00, so it's an n times 1 times n times 1 matrix. So this is an invertible n times n plus 1 times n plus 1 matrix with coefficients k. And then we can use this to define an isomorphism of Pn to itself, which is also a polynomial map. So the map just works as follows. So we have a map like A from Pn to itself, which sends, say, a vector. So the class of a, so if B is a vector in an plus 1, we can put the class of the vector B, and it's sent to just we apply this matrix to this vector, no, just no, and we take the corresponding point in projective space. So this is certainly a well-defined map. If we multiply B by some, or the coefficient, or the coordinates of B by a constant, the whole thing is multiplied by a constant. A is a linear map. And it's also a polynomial map. Namely, how would I write it? So I could write, no, I can write it as given by n tuples of polynomials. So I can say that A is given as a A 0, 0, x0 plus A 0, 1, x1 plus A 0, n. Xn is the first coordinate because it just says that if I have the, if my point B is B0 to Bn, then the first coordinate in the image is this, which precisely means that I apply this matrix here, and so on until A n0 x0 plus A n x. So this is so this and therefore it's a morphism. From Pn to itself, and also clearly it is an isomorphism because obviously its inverse is given by the inverse matrix.
We didn't assume that it is inverted.
Yeah, I wrote inverted. But maybe I didn't say it, or I wrote it in unreadable way. But anyway, these hieroglyphs here are invertible, and therefore we are assuming it's inverted. Sorry about that, but well, it's not much better, but anyway, now you know what I said. Okay, so this is an isomorphism because its inverse is equal minus. No, you see, I need invertible even for this to be a morphism, not just for it being an isomorphism, because I shouldn't have. There should be we shouldn't have things at the kernel. I mean, there should be nothing, if the kernel must be 0, otherwise this is not a morphism, it will be defined outside the kernel, outside the projectivization of the kernel. Okay, so this is of some importance because, so somehow basically, these are, so there are two statements. So the first one is that one can show, but you will not, all isomorphisms from the n to itself are such projective changes of coordinates. So what this means is, so this obviously is a kind of very trivial morphism. I mean, just put down a matrix. But if you want an isomorphism of Pn to itself, these are the only ones which are there. Okay, so this tells us that projective space doesn't have so many. What it also means is that very often one makes some construction which are up to projective change of coordinates. So you define just a morphism from Pn to Pm, but this is, after choice of a basis or something like this, which precisely means up to projective change of coordinates. So somehow these are the morphisms which we don't care about, which we kind of automatically assume we put something in normal form by using this. Okay, so okay, so basically, if we have in particular, if we have a morphism maybe from a subvariety of Pn to a subvariety of Pm, then maybe when we define it, we wouldn't precisely, we would define it maybe only up to projective change of coordinates, both in Pn and Pm. That's actually how one will do it later. I mean, I just want to say it. But anyway, and in addition, we know, I will not prove it because it's not, we haven't developed the tools, but one can show that these are all the morphisms that there are not more.
Is this related to the global functions on the Bm is just as a constant?
In some complicated way, but not directly, no. In the moment I didn't try to look up the proof, so therefore I don't even know, but it is, yeah, it has something to do with it, but it's not straightforward like that. Okay, and I want to give one more example, which is just another kind of a curse, which is the projection from a point. So in this particular case, I just choose my point, so that this point. And so the projection from P, Q, is the rational map. Just if I take the coordinates, I write the coordinates x0 to xn, it's just x0 to xn minus 1 from so n minus 1, which will actually be, you can easily see that it's defined, the only point, so these are, the only common zero of these things is this point, so this is defined on Pn minus q. In particular, it will also be defined on any subvariety x in Pn which does not contain q. Okay. So the picture that you can have in mind is that it's really like a projection. So if we identify Pn minus 1 with a subspace 0 set of say xn, in Pn, so just by sending a point x0, a0 to an minus 1 comma 0, so a0 to an minus 1, basta. So it's certainly bijection. So if we use this to identify it, just in our minds, this projection is just the projection from this point. So we just, between looks, we have our point Q here. Here we have this this 0 set of xn. And if we have any, this is our x, then it somehow the map is given by connecting with this point, and it will somehow hit this, and this will be the image point. So we have somehow get something similar there. Okay, is given by this. Sending point P in Pn without Q to the intersection point of the line PQ with this. Okay. Now you can work out that this actually is true if we're just writing down in coordinates what it means. And in principle, instead of here, I've just told you what the projection from Q is, but obviously we could also look in a suitable sense to the projection from any other point. And then the idea is you can use projective transformation or projective change of coordinates to by composing with it, you can assume that your projection was precisely this one. So up to projective change of coordinates, there's only one projection from a point, which is this one. Because you can use a projective transformation to move this point to there. Okay.
But actually we need more than moving the point, we need to moving a segment.
Yeah, well, you need to move the point and the complementary plane, but you can do that. So what you need, to project, normally you would say you want to project from a point to a hyperplane which does not contain that point. And you can find the linear transformation which moves that point to this point and that hyperplane to this hyperplane. And in the same way, you could also project from any linear subspace, so the intersection of several hyperplanes like that. And again, then you can assume that this subspace is just the zero set of x0 to xn. Okay. So this was, I think, all the examples. So now I'm coming to the next little thing, which is easy. Very slow, but anyway. So so now I wanted to talk about products. So it's basically just from my point of view, it's mostly looking at morphism in another way. So, but it's say products. So it's useful to be able to define and study products of varieties. Somehow x times y of varieties. This has many applications. So the most simple one, the most useful one is maybe the following. So if phi from x, y is a morphism, then I can look at the graph of phi inside x times y, and we will see that this is a closed subvariety of x times y, once we know what that means. And so, knowing the morphism, if we know everything about the graph, we know everything about the morphism. So we can therefore study morphisms, as varieties. I mean, you can use properties of the graph to study this.
But what about the converse?
Which one?
If we have a closed subvariety of the product, does it correspond to?
No, certainly not. No. I mean, you can see that if you have a subvariety here to be the graph of a morphism, it means that if you project to x, it must be, you know, 1 to 1. There's only one point over, you know, every point here. In fact, the projection to x must be an isomorphism. But if you have a subvariety of x times y whose projection to x is an isomorphism, or x, yeah, then it's a graph isomorphism. Okay. Okay, so the graph. So can use this to study. Fine. So there are also some other reasons which we should see later. So let's do this. There in two cases. First, we want to look at the case that we have affine, that x and y are affine. Then it's kind of trivial, because if you take the product of two affine varieties, it's easy to see that just the set theoretic product of them is just an affine variety. And then in the projective case, it's slightly more complicated. So products of affine varieties. So, definition. So let x in the n, y in the m be affine varieties. So then their product is defined to be their product. So the product is x times y, which is just equal to the set of all pairs. So say P, comma Q. But I do this now, so this lies in AN, this lies in AM. So therefore x times y lies in AN times AM, which is AN plus M. With P in X, in Q in. Okay, so that's the product. So just a set theoretical product. So now we want to see that this is also, you know, an affine variety in AN plus M. So we denote, say, x1 to xn, the coordinates on the n, the first factor, and y1 to ym, the coordinates on the second factor, the m. And we can, you know, x is the zero set of some set of polynomials, so we can write x equal to the zero set of some polynomials f1 to fl, where the fi are polynomials in the first set of variables. From the same way, y is the zero set g1, g whatever s, where the gj are polynomials in the second set of variables. And then, so this is in AN, this is in AN. And now x times y, when does a point lie in x times y? When x lies in x and y lies in y. So if I want to use a subset of AN times AM, we just have to put both conditions. So this is therefore the zero set of f1 to fl, g1 to gs in AN. Now obviously this is a polynomial just in x1 to xn, so I view it as a polynomial in all these variables which doesn't depend on those, and so this makes complete sense. Okay, and this is obviously a closed subset. So but we would like it to be a subvariety. That's not obvious here. We just see this is the zero set of some polynomials, this is zero set of some polynomials, so this is also the zero set of some polynomials. So it's closed, but it could have many irreducible components. We certainly don't want that. So now we want to see it's irreducible. So show x times y is irreducible. And again, it's this is some kind of topological statement. So we will want to show it in a way that we can use the same proof in the projective case. So we make a statement of topology. Okay. Maybe first, let me see, we make a little remark, which I think which is kind of trivial, but I want to use it. So just that p from x to y be a continuous map. And x irreducible. Whatever. So these are x and y are topological spaces. This is a continuous map. X is irreducible. Then p of x is irreducible. I don't know whether this was a homework exercise, but I think not. And that's almost completely trivial. So assume p of x is not irreducible. If it's reducible, then we can write p of x is equal to y1 union y2, where both yi are closed subsets of p of x. And none of them is equal to phi of x. So thus I can take the inverse image. So x is equal to phi to the minus 1 of y1 union phi to the minus y2. And obviously none of these two is equal to x. Okay, so it's just a trivial application of the definition. Anyway, I just wanted to, as a kind of preliminary thing, and now I come to my statement. Here. So lemma that x and y be irreducible topological spaces. Irreducible topological spaces. Assume that the set x times y has a topology such that, so first for all points p in x, we have that the map jp from y to x times y, which sends the point b in y to p, that this is continuous. And the same for the other one. So for all q in y, we have that iq from x times y, which sends point a to a comma q, is also continuous. Then it follows that x times y is reduced. Okay, that's all. So you see, we have some kind of very minimal requirement here. So we take two irreducible topological spaces, and we have this kind of very obvious requirement that if you just embed, we have the x times y, this is x, this is y. If we fix a point q here, we just embed x as this fiber, and this map from x to this should be continuous. Somehow one would expect that for any reasonable definition of the topology of the product should be true. And the same here, if we take a point P here, then the map from y to this slice should also be continuous. Then the product is irreducible. Okay? Okay, so let's prove it. Some kind of abstract.
Sorry, just this part about reducibility. Why the inverse image is not all of x?
Well, you know, if we have said that, you know, this is the image, no? So that means, so if the image is the union of these two things, and none of that is equal, so as it is the image, every point comes from somewhere. So, you know, so if downstairs they are not equal, then upstairs they can't be. It's not the statement that y would be equal to the union, it's the image. Now, obviously, that would be nonsense to say that if you have a morphism to x from x to y, or a continuous map from x to y, then y must be irreducible. I mean, that's nonsense, because you could just map to one of the components. Okay, so let's prove it. So we make an indirect argument, so we assume that x times y can be written as S1 union S2, where the Si are closed subsets. Okay, so this would mean that x times y is reducible. Now we somehow have to we want to deduce from that either x or y is also reducible. And we do this by the following little trick. So for I equals 1 and 2, we put Ti to be the set of all points P and X, such that if I take P times X times Y, that this is contained in Si. So we want somehow, we have here these, you know, divide this into two pieces, and we want that the whole fiber over P, so everything, so here we have P, so we have divided this into two pieces, so this is S1 and the other one is S2, and then we want the whole fiber to like note. So we can write this as the intersection over all q in y of I q to the minus 1 of Si. Because I q to the minus 1 of Si means that this precisely means that the whole fiber, you know, so is this correct? So we, that's correct, no? Yeah, let's see. So this condition means that we want that the whole fiber lies there. That's precisely what intersection over all q and y means. That iq to the minus 1 means we look at all the points in x so that the whole fiber lies there. This is precisely this thing. And note that this, therefore, for as iq is continuous, according to our assumption for Q. This is an intersection of closed subsets because it's the inverse image of a closed subset by a continuous map. So this is an intersection of closed subsets, so it's closed. We find we get that Ti in F is closed. So, and I think we had this homework. I don't remember the homework that you were supposed to give me today. I hope I gave it to you. That it follows if, let me just say, well, maybe I don't need it. Maybe I can just say it. So as this also the map GP is continuous, and why it's very useful, so the image, so this was what I just said, JP of Y, which is just P times Y, is irreducible. This is by the remark I just made. And so now I wanted to say this, this remark, this homework. The statement is if you have a closed subset of an irreducible subset, then it must lie either in one component or in the other component. That's obvious because you can write it as the union of its intersection with one component and with the other component, and being irreducible has to be equal to 1. So, okay, so thus we find that P times Y must either lie in S1 or P times Y is in S2 for all P. So for each P, we find that P times Y is in S1 or P times Y is in S2. For all P in X. But so that says, however, that that X is the union of T1 and T2, because either P times Y lies in X, lies in S1 or it lies in S2, so it's precisely that. So that means, so thus, we have that X is equal to X1 union X2, and by T1 and T2. And clearly, we have that both Ti are not equal to X. Because otherwise, you know, if Ti is equal to X, then by definition, Si is equal to X times Y by our definition of Ti. And so it follows that X is equal. Okay. So this gives us this argument. And so now we want to apply this to our situation for our affine varieties. So corollary if X in N and Y in M are affine varieties, then X times Y in the N plus N is also and final height. Well, now we just have to see that our assumption is fulfilled. Our assumption was that both these embeddings of x as a slice in the product and y as a slice in the product should be continuous. And we will see that they are morphisms and therefore continuous. Yes?
Sorry guys, excuse me.
Have you signed something?
Yeah, but I'm living now and this should be same now.
Okay.
German.
Yeah. It works.
How will I teach
What? Okay, so where was I? Ah, yeah. So now we have to show, obviously, that this assumption from before, so that these map from x to x times y, and so on from y to x times y that we had are both continuous. And we show this by showing that they are morphisms, and that's actually quite trivial. So proof. So to show for P equal to, so well, maybe I don't say to show, it's obvious what it's to show. So let Q be a point, which I have the coordinates B1 to M, be a point in Y. So then if I look at the map IQ from x to x times y, which sends the point P to P, comma Q, what is it? Well, it's just can be written, is given by, take just, if I put the coordinates here as x1 to xn, then it's just given by x1 to xn, comma, e1 to en. So this is just the thing. You send the point P, so if the point P is a0 to an, it's sent to a0 to n, which is just given by these coordinates. So it's just this. So you can see these are all regular functions. These are polynomials. And these are constants, so thus it is a morphism, and therefore continuous. But obviously in the same way, we have that the other embedding is continuous. So the lemma applies. Okay, that's all. Maybe should also mention, good for this exercise, if x in an, y in en are quasi-projective varieties, then their product will also be a quasi-projective variety.
But we haven't defined the product of quasi-projective varieties.
The set theoretic product.
Okay.
No, with product, I mean here, okay. So, yeah, I should have said maybe, okay, so.
Me quasi-affine or quasi-projective?
Ah, sorry, I meant fine, obviously, yes. Otherwise, you would be very right. And it certainly, this wouldn't have been an exercise at all. That's actually something we will deal with partially today and then afterwards tomorrow, next week. So then it's, and this is somehow obvious because it should be quite easy. It's a modification of what we have done here, so that that the product is quasi-affine. So if this is quasi-affine, it means the zero set of some polynomials minus the zero set of some other polynomials, and the same here. And you can easily find out that this is the zero set of certain polynomials minus the zero set of some other polynomials. You can figure it out from these what we create here. And the fact that this will be irreducible if x and y are irreducible is the same proof as before. Okay, but yes, certainly quasi-affine. Now, finally, we want to prove some kind of universal property. So basically, we also will need this for the projective case. If one has a product, or for many other constructions, one doesn't really care what precisely the points of the thing are. What is important is, either what are the maps to this thing, or what are the maps which come from the thing. So in this case, it's the map which map into it mostly. And so there's a certain universal property basically saying that a map from any variety to x times y is the same as a pair of maps, one from the variety to x and one from the variety to y. So that's write this down. So the universal property. And then you will see later that this is, when we use products, this is most of the time the only thing we use. We don't go back to the definitions. It's always about this. So universal property and position. I don't maybe write it super precise as a universal property in the categorical sense, but it is equivalent to that. So let x in the n, y in the n be defined varieties. This would also work with quasi-affine, but I do just do it for fine. So first, the projections. So P1 from x times y to x, and P2 from x times y to y are morphisms. And secondly, if z is any variety, so quasi-affine or quasi-projective, the morphisms z to x times y are precisely given as follows. Precisely the following maps. So I write them as f comma g from z to x times y. So where we send a point p in z to the pair f of p comma g of p. For morphisms f from z to x and g from z to y. So we know precisely, if we know what the morphisms from f to x are, and from z to x and from z to y, we know also the morphisms to the product, and in some sense also vice versa, so also the other. Okay. So the statement almost takes longer than the proof. So, I mean, as an exercise, one could generalize this to the case with x and y are quasi-affine. So it will be the same. So, So I write as before, x1 to xn for the coordinates on the first vector an, and y1 to ym for the coordinates on the second vector am. Then, obviously, so I do the first one. The first projection is just given by x1 to xn. No? Just send a pair of a point. So this x1 to xn is just precisely the identity on an, and it maps this to 0. So it's just that. And p2 is equal to y1 ym, and these are clearly morphisms. Okay, so that's so now we have to show that the morphisms are precisely this. So we have two directions. So if we have a morphism from z to x times y, we have to show it's of this form. And conversely, if we have a pair of morphisms from z to x and to y, we have to show that this thing is a morphism. So that's h from z to x times y, the morphism. So, what does this actually mean? What will this f be? F is just the corresponding map to x, the first component of the map. It just means it's the composition of h with p1. So we put f equal to p1 composed with h, g equal to p2 composed with h, and h is a morphism, p1 and p2 are morphisms, so as a composition of morphisms, these are morphisms. So this was from z to x, and this was from z to y, and these are morphisms. As compositions of morphisms. So therefore, now if I look at h of p, what is h of p? It has two components, one in x and y, and one in y. So the first one is p1 composed with h of p, so for all p in z, and p2 composed with h of p, so equal to f of p g of p. Okay, so that means h is equal to this morphism f. Okay, so no. And conversely, now conversely we have to see if we have two morphisms, f and g, from z to x times y, then this thing is a morphism. So conversely, that f, you can write it as f1 to fn from z to x, the morphism. So the fi will be some regular functions on the whole of Z. That's, we know all morphisms are of this form, and the morphisms to Pn are of the form they are given by by integrals of regular functions, and G equal to G1 to Gm Z to Y, the morphism. That means that all the Gj are also regular functions on Z. Then obviously, if I take the map Fg, this is just given by putting these things together. So this is just F1 to Fn, G1 to Gn. So it is given by an n plus m tuple of regular functions. Okay, so we just have used directly the definitions to. Okay, so much for the case of, for now, for the case of defined varieties. Now let's look at the projective case. So we want to define the product of projective and quasi-projective varieties. Now, if one want to do it in a slightly more sophisticated way, one would say we define what an abstract variety is, which is, something more general than what we consider, and then you just take the set theoretic product of x and y, like here, and we give it the structure of an abstract variety, and then this will be the thing we consider. And then the thing which we do now, which is instead embed this product in some other projective space, would be just a property that this abstract product has that it can be embedded in a certain weak projective space. We instead do not want to go to the abstract varieties because it's technically a little bit more complicated. So instead, we define an injective map of the product of Pn and Pm into some other projective space, and we call the product of Pn and Pm the image of this map. And then we always we identify this product with the image, and we work with that. So the image will then automatically be a projective variety, and if we have if you want to define a product of two projective varieties, we just take the image of these varieties under this map into another projective space. So with our definition, therefore, the product of projective varieties always lies in projective space, but strictly speaking, it's not set theoretically the product. It's bijective to the product, but it's not the same set. But anyway, you can live it. So let me now do that. So this other way, the abstract varieties would be a bit more clean, but on the other hand, there are some technical difficulties, and I only tried once to talk about abstract varieties, and nobody understood anything, so I have decided to not try it anymore. Okay. So we talk about the Hegel map. So this is after Benjamino Husserl, who was an Italian mathematician who came up with this. So I think he's one of these this school of Italian algebraic geometers from the beginning of the 19th century, which developed all this wonderful theory and had very few correct proofs, but the theorems were usually correct. No, there was this Italian algebraic geometry which was very successful. It only had this little bit mystical qualities that somehow if you're not part of the school, you couldn't somehow understand. And there was a lot of intuition involved, which was usually correct, but not always. I mean, some of the Italian proofs were also wrong, but most of the proofs, many of the proofs were not complete. And then later, when there were foundations for algebraic geometry, all these things were reproven in the modern fashion. Okay, but I mean, this is not so difficult, but I mean, at least, but he was one of the people in this. And I mean, here's some, it's not, there's nothing wrong with it in some sense. There were no proper foundations, so it was not possible to prove certain things. The methods were just not there. But they still managed to prove them, and their theorems were correct. So in some sense, it's a very good thing. But on the other hand, eventually one has to know what one's talking about, and not just feel it. Okay. So what is we want to study product of projective varieties. So the difficulty is that if I take the product of two projective spaces, this is not in a natural way a subset of some projective space. I mean, what does natural mean? It's just not a subset, no? Not a subset of some other projective space. But our way out is we find an injective map from this to some projective space, and we'll instead of working with this set theoretical product, we work with the image.
Because Bn is just a n plus 1 with some identification, and the same for Bn. What if we take a n plus m plus 2 and define a new relation like separately?
No, it won't work, no. No, I mean, okay, no, but that's, I mean, this still doesn't, you cannot do so if you want to do this, you would have to take Pn, so you would have to take an plus 1 times am plus 1 modulo k star times k star, but that's not a projective space. So the equivalence relation does not make it projective space because we have two kind of functions. So that quotient will precisely give you Pn times Pn, but it doesn't give you some projective space here. I mean, it's just not, but I mean, in some sense, okay. But obviously, you could also directly work with this and say you now view this as an algebraic thing, and you want to say what should be the closest. I mean, anyway, we'll come to that later. So we will show there's an injective map. So Pn times Pm to some Pn, and I can already resolve the mystery. It's n plus 1 times m plus 1 minus 1, so rather big space. Whose image is a closed subset. And so if we identify these, this becomes a projective variety. Okay, so let's carry this out. I have to tell you what this map is, and that's the so-called Segel invention. So first I shall make the definition. Again, write that n is equal to n plus 1 times n plus 1 minus 1. And so we take that x0, so xn, if the coordinates, the homogeneous coordinates on Pn, y0, so ym, the coordinates on Pm, and as you can see, the number of coordinates here would be n plus 1 times m plus 1, because the dimension is space 1 less. So we take, so they correspond to pairs of numbers ij, with I and j between I between 0 and n, and j between 0 and m. So that c ij, I from 0 to n, j from 0 to m, be the coordinates on Pn. No? These are precisely n plus 1 times n plus 1 coordinates, as many as you need for this projective space Pn. P large n. Now define the map. Sigma from Pn times Pn to Pn, just coordinate wise. So the point A0, so projective coordinates A0 to An, E0 to Pm, is sent. So the ij coordinate of in Pn is just the product of the ith coordinate here and the jth here. So this is, I write it like this. So this is ai times bj for I equals 0 to n, j equals 0 to m. Okay, just send this thing to all the products of all the coordinates. It's a kind of stupid map which makes it, which embeds it in a very big space, but okay, that's what we do. Okay, this is the Segel embedding. So first we have to see that this is well defined. Well, in that sense, that's obvious. So what it means, it doesn't depend on the representative. So if we multiply, maybe I just say it, if we multiply every coordinate here by the same number lambda, and every coordinate here with the same lambda mu, then we multiply every coordinate here with the same number lambda times mu. So if we do this, we are sent to the same place. So if we replace this by another representative and this by another representative, we replace this by another representative, but it's the same point in projective space. Okay, so this is where. And so I say, so we denote sigma equal to sigma nm, the image of this map. Now I claim to you that this was an injective map, so I have to show it. I want to show this map is injective and the image is a closed, first a closed subset, later we'll see it's a closed subvariety. So the following proposition.
I'm just curious, is this a projectization of the tensor product of the affine vector spaces?
Okay, let me see.
Because this is just like we are multiplying a matrix product of a column with a row.
Yeah, no, okay, you could say, I think you could say that, yes, that it's just, after all, this is, yeah, you could say it's a productization of the tensor product of these vector spaces, this is correct, yeah. But, you know, I don't see this as a simplification. Yeah. Okay, yes. And, okay, yeah, that's correct, but, you know. So if you find that easy, that is. So now the proposition is first, sigma is injective, and the second statement is that the image sigma, so in ENM, En, is a closed subset, namely it can be written as a zero set of the following polynomials. I take Zij, so times Zkl minus Zil times Zkj. I take these equations and these these are all coordinates, so I multiply them with all these quadratic polynomials for all possibilities. So I, k goes from 0 to n, and j, l goes from 0 to n. We look at all possible products like this, and the common zero set of that we claim is sigma. So in particular, it's a closed subset. Of yeah. Okay. So let's see. First one is much easier, but not much easier, slightly easier. So we want to claim that this map is injective. So we have to see that if two things are mapped to the same, then they were already the same. So, so if sigma of A0 for An.
But first, this will define it because we can get the zero, the map itself. We can get the 0 point. For example, if I have
Okay. So where? Now what does it mean? That it's well defined means that so the one thing with well defined is if what you really only need, but I will also answer your question, is just if I multiply this by lambda and this by mu, then this is multiplied by lambda mu. Okay, so that means it only depends on the class. But this also will imply that if this is not the zero vector, or this is not the zero vector, then this is not the zero vector.
But for example, 1, 0 and 0, 1, neither of them is a zero vector, but when we...
No, there will be one coordinate which is non-zero.
Okay,
you don't need that all coordinates are non-zero, you have to find one. So if here you have one non-zero coordinate, and here one zero coordinate, then obviously, so if the ith coordinate here is non-zero, and the jth coordinate is non-zero here, then the ijth coordinate here is non-zero. So it always this way. So if sigma is like this, so say A0 prime assume we have two such things are mapped to the same thing. What do we have? So then it means, so this must be the same point, so it means that up to multiplying by a constant, the vector given by all possible products of these must be equal to the product, the vector given by all possible products of one here and one here. So this means then there exists an element lambda in K without 0 such that AI prime Bj prime is equal to lambda AI Bj for all I and j. So there's one lambda which does it for. Now I could choose, say, so we can choose I0, J0, such that, say, A I0 prime, B J0 prime is not 0. No, these are both non-zero vectors. We can certainly find one such that the product is non-zero. So in particular, so thus we have that B J0 prime is different from 0. But what? So in particular now we can put here. We can look at the special case here that we have B0, that we have J0. So then it follows that AI prime B J0 prime is equal to lambda AI B J0, or we get that AI prime is equal to lambda times B J0 divided by B J0 prime, because now we know this is non-zero, times AI. So this is just some number. One number, it's always the same, it's a fixed number, and it works for all I. So that means that the vector A0 prime until AN prime is the same, is its same point projective space as the point projective space A0 to AN. Because I just have multiplied every component by the same number. Alright. So that's the 0 prime n prime is equal to A0. But not like this, obviously, so as a point in projective space. And obviously in the same way it works for B, in the same way. We have that B0 to Bm is equal to B0 prime Bm prime. So the map is the J. So now I want to show the second statement. So we have this nice zero set, so let me give it a name. I call it W. So just to show that W is equal to sigma. So it is clear that sigma is contained in W. Why is that? So if I'm in the image, the coordinate Cij is AI times Bj. So what it says is AI times Bj times AK times BL should be the same as AI times BL times AK times Bj. That's trivial. Okay? Just if we, this pair is just, something like that is just Zij just gets replaced by AIBJ, and then this is a tautology. Okay? So this direction is clear. Now we have to show that this is precisely the image. So that if something lies in W, in the 0 set, then it lies in the image. I have to find the A and B which are sent to it. So I call it maybe AIJ, I from 0 to n, j from 0 to m, be an element in W. So we can choose some, I mean, this is a non-zero, this is an element projective space, so one of the coordinates must be non-zero. So we choose K and L with A, K, L different from 0. Oh. And then let's just see. So we have this. Now I want to see why it is in the image. So if I have this Aij, I from 0 to n, j from 0 to m, obviously I get the same point if I multiply every component by the same element, namely this one, this non-zero element. So this is obviously the same as the set is Ai j times AKL, and we still have I goes from 0 to n, j goes from 0 to n. But now we can apply the relation. Aij times AKL is the same as, what is it? AIL times AKJ. So this is the same as AI, what is it? L times AKJ, where still I goes from 0 to n and j goes from 0 to m. But now you can see what we have done. We have this thing, and here the I runs, here the j runs. So we have just taken, this is just sigma of this vector given by this thing when I runs times the vector given by this when j runs. So this is just sigma of a 0 L until a NL B K 0 until B K N. Okay, so this is just, so this step here was by relation, because it's in W, and then we just find this. And so it lies in the image. Okay, so this is proof. And okay, so maybe that's enough. So we